Okay, in this next section, they ask us to go ahead, identify the tail of the test, find the p-value, and then decide whether or not we should reject the null hypothesis. And before I go through this, I do want to talk a little bit about what the p-value represents. And I'm going to use items from question 17 here, and I will go back to how I determine what tail test this actually is. But if we were to go ahead and put in our standard normal distribution here, what the test statistic represents, and here is the test statistic. So that's what we had computed in our last set of examples. It represents how many standard deviations away from what our claim value was that our sample result was. So what's the likelihood of getting our sample result or something more extreme if our claim value was indeed true? So here our test statistic is 1.0, and we're going to see that in example 17 that this is a right tail test. So the size of the right tail is the p-value. So the p-value and the test statistic go hand in hand. The test statistic is the number on the number line. The p-value is the size of the tail that it cuts off. And again, area under the curve is probability. So going back to question 17, the first thing we need to do is determine, is this hypothesis test a two-tail test, left tail test, right tail test? And to do this, we have to go ahead and identify our claim here, and our claim is already in symbolic form. So next we can go ahead, and if we have that, we also want the opposite, and the opposite here is less than or equal to 0.3. And we can use these items to set up our hypothesis statement. So if it's P in the claim, it's P in the hypothesis statement. If it's 0.3 in the claim, it's 0.3 in the hypothesis statement. And what goes between them in the null? Equal, because it's always equal in the null. And then we need the strict inequality in the alternate hypothesis, and that is the greater than. So what we have here is, since it's the greater than there, this represents a right-tailed test. So we've taken care of part A, and then now part B is find the p-value. So if we're going to go ahead and find the p-value, there's a couple ways we could do that. We could go to StatDist, bring up the normal distribution, put in 1.00 for the test statistic for the z-value, and take the area to the right. Or we could go ahead, work off table A2, and on table A2, we find that the area on table A2 for 1.00 is 8413. And to go ahead, that's going to be the area to the left. We want the area to the right. So what we're going to need to do with that is subtract it from 1. And that gives us 0.1587. And that looks about right for the size of our tail here. So the size of this tail is 0.1587, which means that our p-value is 0.1587. The last thing that we need to do here is go ahead and decide whether or not we're going to reject or fail to reject the null hypothesis. And to do this, we're going to need our rule of rejection. And our rule of rejection requires us to have a level of significance, which is alpha. So our rule of rejection is always phrased this way. Reject null hypothesis if p-value less than or equal to whatever the value of alpha is. So if 0.1587 is less than or equal to 0.05, we would reject the null hypothesis. If it's not, then we do not. And 0.1587, that's close to 16%, definitely not less than or equal to 5%. So in this case, we fail to reject the null hypothesis. What this means is that our sample result is consistent with the idea of a true proportion being 0.3. That's what we assumed for this question. We assumed that the null hypothesis was true. So we assumed that the true proportion was 0.3, and then we found the likelihood of getting our sample result or something more extreme. They went ahead and did the computation for us and given us the test statistic. And we could use that and the tail of the test to figure out which area under the curve we need. And that's what we end up making the decision off of. And what's nice about the rule of rejection for p-value is it is always set up this way. More importantly, the inequality that's in this, it always works in that direction. Again, this comparison here, when we were looking at using probability to determine if something was significantly high or significantly low, we were wondering, was the probability less than or equal to 0.05? So again, this is just a continuation of what they've been having us do for statistical significance, for significantly high or low values, all the way back through the chapters that we covered.